Hi, welcome to the Online Proposers Day to the Lifelong Learning Machines. So there are a few ground rules, and the BAA was already posted, and because of that, I will encourage you to have an open communication with me, but this will have to be through the particular inbox that you will see on the BAA. So please feel comfortable to contact me at any time according to these rules. So let's start to see what the lifelong learning is about. And since we're in a very particular type of field, which is artificial intelligence, there has been lots of media coverage on this. Let's see how we look from the outside, which will be an interesting way to reflect on where we are. So you can see that AI success is appearing everywhere, from the Go game and the previous games of chess and pokers and Jeopardy and Atari. And if we go to image recognition, there is nothing as good as the current AI. Human cannot defeat it. So we see the AI great successes on one side. On the other side, we see some limitation. So we can see self-driving car, it happens to Uber, it happens to Google, to other companies, that they went into collisions, and typically they were cleared out of fault. So it was not the self-driving car's fault. In one case, it was a car that bumped into that. In another, it was a manned vehicle that ran into red light. And it seems like the limitation was only to the point that the car didn't know how to handle with these people that drove not in a way they expected. A very nice way of explaining it was on the New York Times after the Tesla car crash. And what they wrote there is that, and let me just read it because I find it very illuminating. The regulator warned that the advanced driver assistance system like the one in Tesla cars could be relied upon to react properly in only some situations that arise on the roadways. So this kind of gives us a little bit of a shake feeling if we have to say buy our cars, but make sure that there is nobody under 23 that drives near you, or make sure that everybody around you is driving exactly the same way that you expect. So what is it that caused some AI to be so successful but other one brittle? So within the realm of self-driving car or the realm of general automatic machines, we realized that we would like the rigor of automation, which is better than what human can do when they're absent-minded, but we would like to have the flexibility of a human. And what do I mean by that? For the rigor of operation, we would like the driver not to text and not to drink, and we can ask that from the computer. For the flexibility of a human that we don't get now from the AI, what happened is that once you program the self-driving car, it's frozen during its execution. So while if you were driving the car, it's possible that another person will go in red light, and accidents sometimes occur, but in other times, some of you may have this experience that you managed to save the day and not to get into an accident because you did something that was not taught to you in driving schools, like stopping in the middle of an intersection or reversing in an intersection or going on the side or doing something that is not very regular just because you understand the notion of an accident going to happen and you try to do ways to get out of that. So the cars, which were programmed in advance, function very well to what they were prepared for. What they malfunctions is not really malfunctions, they're just operating in real-world environment, and they're bounded to this experience that they had before. So the question comes immediately, is it possible for us to have a fast fix for that? Is there a way that when the car drives, and it get into accident, then we stop the car, we take this information about the accident, we give it back as a training example, and then the car will next time be better. So there is an issue in machine learning that does not allow us to do that, and this is called the catastrophic forgetting. So what we have in catastrophic forgetting is that if we have a neural network or another machine learning system, we learn and adapt all parameters. So we did it to a training set, and now we come with a new training set of these examples that we want to make sure that the car or the system will know. But once we take the new set and learn it in the same system, we actually overriding on the parameters that we had before. So what happened is that we catastrophically forget the same information that we had before, which the car was so good most of the time about. So there is no way to take only the new information and add it, just that one. What we really have to do is to take the new data and the old data and put it all together and restart training the machine from start. So there is no real way now for an easy fix. We need something else, something better. So what is our plan to improve AI within this lifelong learning machine? So the lifelong learning machine is a program where we want to develop a fundamentally new machine learning mechanism that will enable systems to improve their performance over their lifetime. So the idea actually was suggested in the 40s when people started talking about AI. They were talking about AI that will be like human, that once we do things outside, we take this experience and it's an add-on, and then we can do better, which is totally unlike what AI started getting to in the 50s and remained there, which once we experience or once we execute, we don't take this information back as knowledge and experience. And this particular of AI that we want now to have is particularly important to the DoD for two reasons. The first of them is we want to have continuously improved performance. And this is if we think that in the DoD, typically we don't have a lot of data for our data set. So it's not like Google or Facebook or playing games online that we can run millions and millions of screens and collect a lot of data. If our data is really coming from intelligence, we have as much as we got. And we have to load our system, our AI, and start putting it outside. So we would really like to use everything that the machine experience and add it as part of the training set so that the machine becomes better and better. So this is one reason. The other reason is even more important and more interesting. And this is about adaptive to new conditions. So in DoD, it's possible that we go ready to the next war with the information of the previous war, which can be different place, different people. And it's not exactly fitting. It's just almost fitting. So if you see on the graph, we have performance on the Y and time on the X. So with training, we become better, our performance become better, and then we go to the real field and we may be surprised. And as we surprise, the machine will start performing less good. And if we're working with the current AI, it will be frozen, so there will be no way to improve it. In the lifelong learning, what our plan is that it will start being bad a little bit, then it will realize, like people, that it's not doing very well and that it's not ready. And then it will start learning as it works to answer to this new surprise. So that's the big goal that we have, the objective for the lifelong learning machine. So in order to do that, we need to have fundamentally new thinking about what can be done in AI. So the classical way that we think about computation or computer science in general is the Turing machine. So in 1936, our genius, Alan Turing, modeled the human calculator into a machine model, into a mathematical model that we called since then the Turing machine. And this machine was supposed to simulate these people calculators on how they work. And the beautiful thing that he had was that there is a main part in the middle that now we call the CPU, and there is a other part, which is the memory, which is stable. And then if we want to do something, we take a program, we load it to this general CPU, and then this program can work on every input-output. So if you want to multiply matrices, we put a program of how to multiply matrices, and we put as an input matrices, whichever they are, and it gives us the right answer in the output. So because this is such a general and such a basic idea, we actually use the Turing machine for any of our current computers that have CPU, memory, and I/O. And we also use this notion in general for our current view of computer science and of AI. What we did in machine learning was a little tiny change, but still within the framework of the Turing machine. So the Turing machine tells us that the program has to be loaded in advance. Machine learning tells us that we want to have a training set and be training on it. So what we did in machine learning, we had this part where we loaded the type of neural network, so everything that has to be there. Then we take the training set and we work on it. So it's kind of like a little bit to the side of the loadable program, but still before execution. And then all this together are pre-execution. Now we're ready, and now we finish to do machine learning. Now we start executing. And that's the current AI, that's the current machine learning. Is it possible to do something different? That's really a question, because in computer science, we're so much used to have the program given in advance. So let's see some machines or some instances where we have lifelong learning. So a classical example is in nature. And we see this beautiful statement that it is not the strongest that survives, but the one that is able to best adapt to changing environment. So we see that nature has this notion of survival based on changes. So what kind of mechanism nature gives us? Well, all know about evolution, which is a way to do updates, but there are actually many mechanisms that allow organisms to change during their lifetime. So I'll just give two examples, but there are many. So one of them is brain reconsolidation. So I particularly love this topic because it has been my field of research for some time. So the idea of brain reconsolidation is this. When you see a new memory, you consolidate it into your brain. Once you retrieve this memory and use it, it can be conscious or subconscious or non-conscious, this memory becomes liable, becomes weak. And at that stage, there is another process that takes this weak memory and put it back in. But once you put back memory after it was not there, it's never going to be exactly the same as it was before. And this is a great mechanism that keeps us in the present. So you can think about looking at your spouse and not thinking every day, oh, you look so much nicer 30 years ago, because you used to the person the way that it looks now, and your understanding is really current at the moment. And, psychologists knew about it for many years. They took a person with PTSD, they talked about this, and it's not that the patients forgot what happened, but they were able to connect it differently. Instead of to be connected to all the trauma around, they are connected now to the psychologist, to the warm sofa, maybe to the tea. So this is one way in which our memory works. Our memory are actually reconsolidatable. They are not fixed. Memory is all about changing. Another mechanism that we see all around us is epigenetics. So years ago, we used to think that the whole information, the whole genetic information is just coming through the DNA strands. And now we know that there can be other ways, which are ways to tell the DNA how to do the transcription, what to use and what not to use. So while the DNA is still holding the information about the genes, there is epigenetic that tell it how to work. And these changes are happening in your lifetime due to things that occurred, and many experiments demonstrate that not only it affects you, but it may affect your children and a few other generations. So if you change things, it may affect the next generation it's going through, and it was actually changed to your program. So nature allows it pretty easily. So we see that it's possible there. What about computer science? So in theoretical computer science, we also have a way of going beyond pre-programming. In fact, in the 90s, my group demonstrated that there is a continuum of computational hierarchy going all the way from the Turing machine to what I called super Turing machines. And this continuum hierarchy can be explained by different type of ingredients. At the time in the 90s, I first explained it by using analog values of rich information instead of discrete value. Later, I explained that it was related to randomness, but in recent years, together with a group of people, we managed to demonstrate that it's actually the possibility of evolving or the plasticity that allows us to go from Turing machine to the super Turing machine. So the super Turing machine is very well-defined class. It's not everything, it's not tautology. And we're able to do many things because of that. So now we understand that there is this theory that tells us that if we modify the program as we go, we can do more than current computers. In fact, to the mathematicians of us, if we're looking at the interactive model, and that does not go like the classical Turing machine of question, answer, but is a machine that works for a long time and has long input and long output, we can actually realize mathematically that with the Turing model, we'll have only Aleph 0 different types of outputs. And when we use the super Turing machine, we'll get 2 to the power of Aleph 0 different types of output, which is much, much more. It's still not everything. It's not tautology. It's not 2 to the Aleph 0, but it gives us much more because of that. And this super Turing is a theory so far, but it has some property that we may see as appearing in nature, like it has this property of using only as much precision as needed. Interestingly, the idea of super Turing was actually hinted to earlier on by Alan Turing. So Alan Turing, in his 50th paper and later in his early 50s discussions and talks, described that he believes that his type of machine and the digital machine is working in disciplined but unintelligent manner. And his contention was that machine will be able to simulate the human mind and be actually intelligent. And he has a whole paper where he argues with people and explains to them that that's likely to happen. He even gives time, which is 100 years from then. So maybe we're a little bit early, but we're going there. So there is an interesting point for us to notice. When we talk about super Turing computation, or when we will be talking about adaptive or L2 computation, it doesn't mean that we throw the previous computation, not at all. We actually build on it. So I'll tell you what I mean. When we have natural system, the natural system run fixed programs. So they run Turing programs. At the same time, they can adapt as needed and then change this Turing program. And then they can actually store this changed program so they can use them as components in the future. So we can still have these programs that we follow, but the super Turing or the L2 have this capability to do something like mega or meta programming in which the organism can adapt. So I would like to give you an example from brain just to see how we can take properties from brain to lifelong learning machines. So if we look at brains, we don't have to think anymore of the classical neural networks because we have plastic nodal network structure, which are not necessarily homogeneous. We have different types of nodes in the brain, different types of neurons, different type of communication. Another thing that we can take from the brain is signaling. In classical neural networks and in classical computer science, we typically think of electrical signaling, and we think about the neurons as a little processor that receive inputs, do some programming on that, and output another signals, which will also be electrical. But in reality, the brain can submit chemical signals. So it can combine discrete and continuous signaling. And why is it so important? Because the continuous type of signaling can not only tell the neuron if to fire or not, but they actually can change the way that the neuron works. So I'll give you an example. Think of somebody else, not you, has an exposure to drugs or is being stressed. So it's not that the neuron will fire more or less just generally, but the whole system is different. The system will actually change the way it works. The neuron will work differently. So the chemical signal is crucial because it gives us this large option of adaptivity rather than just small ones that we get from electrical signals. And the last points that I'll mention here that we can see from brain is a point that tells us perhaps how hard is this program and how hard your job will be when you join this program. And this is the ability to select which input will drive adaptation. So in classical machine learning, we have the training set, and it can be supervised or it can be even unsupervised, but the training examples are given to us and they're already processed and given to us in a beautiful way, and we know that we have to make the machine accept them. When we have our brain, we see all the time things, and we don't want everything to change all the time. We'll have to make a decision when we want to start adapting and what from all these circumstances is taken to my brain so that I will start adapting and changing. So there is a trick here, which is one more step from just training set, including if it was unsupervised. So let's go to the program now. So the vision is up till now, the machine learning was we prepared the code, then we trained, we started operating, went to the field, and we had only a rigid model. What we want to have is in 4 years, we have a machine that started with a prepared code and training, but we have flexible models. So we continue going to school all our life and improve. This is the vision. And the way that the structure will work is the following. We'll have 2 different technical areas. The first technical areas will be lifelong learning system, and it is focusing on creating these type of systems either in computer, in hardware, in synthetic biology, but actual system like that at the end. And the focus will be on people which are computer scientists, maybe physicists, maybe engineers, maybe some help from biologists or psychologists, but all around AI. The second TA is different, and here we're going to ask biologists to join us, and also physicists, and also people from all life sciences. You have all kind of lifelong learning systems, and you deal with them all the years. We computer scientists, we cannot even think how to do that. What we want you to do is to go to your system, try to realize what's the mechanism that allows this lifelong system to happen. We want you to study mechanistically to the point that you can take this mechanism and write it as a code, as an algorithm, as a program, so that we can take this program and have some property, some facets of the lifelong learning machine that we would like to build. So let me just talk a little bit about each TA and how to write your BAA. So there are many ways that we can think of lifelong learning machines, and I defined 5 particular properties which are partially overlap, but each of them stress a particular feature that I would like to see. The first is continual learning, just the fact that the system are capable of learning during their execution. The second one is the capability to adapt to new tasks and circumstances. So that means that we have we learn previous skills and we want to be able to adapt them and to change them to use in novel situations and without forgetting the previously learned tasks. So if you had a robot that worked in your kitchen and first you taught it how to cut vegetables and then you taught it how to stir things, you want it still to remember the previous thing. So there is some overlap with continual learning, but it's not all that. The way that we think about why a system will be able to adapt to new circumstances is because this continual experiential type of learning. And perhaps there is a point to mention this very interesting research that demonstrated a cat that is going around in the environment and searching it. And this cat will learn very much about the environment, will know everything about it. And you take another cat in a basket that is taken exactly to the same places where the first cat went to, but that cat does not control and does not ask the question, where should I go? Maybe I'll go here because I have this idea for how the environment looks like. It's just taken. So the two cats did exactly the same thing, but one did it actively, like lifelong learning, and one did it passively, like receiving the training set. And one understands and one doesn't, which is maybe the idea that we'll get on in that second one. The third one is the goal-driven perception. That's the hard question about how to view input. And the very general suggestion that I give is the following. You will have to decide which input are going to change your machine. Think about the machine as having a goal, and it treats the input as relevant to its goal. I'll give you an example. Let's say that I'm not so hungry and I see crumbs of old cereal on my desk. It will not excite me. I may even throw it to the garbage can. But if I was starved for 5 days and I see this bad cereal, so my goal-driven has changed, this is now a food and I can eat it even without milk. So this is the type of things that we see in animals, and that is the type of thing that may help you when you think of how to treat the input. The fourth one is a very important point. We call it selective plasticity in short. And this is about balancing stability and plasticity. If you have a machine algorithm that never changes, you cannot say that it learns. On the other hand, if you have a machine that all the time changes with every input, it also doesn't learn. It more like mirrors the input to you. What you want to have is this stability and plasticity balance. And this is the selective plasticity. This leads us to the last one, but not least, which is safety and monitoring. So all over AI we have the question of safety, and in lifelong learning, maybe there are particular issues of safety that are interesting. In general, when you will define your system, let's say a system that have to understand speech or a system that has to help drone to move, you will define what the target is. But so it will never, like the system that will do understanding of speech will not be expected to start drive robot. So it will stay where it is. But you still want to have some more safety internally and still, since it's a new program, externally by a human monitoring. So there'll be part of the program where you will see in the BAA where we'll particularly focus at that time on safety and monitoring, while at the beginning we'll focus more on the first four. I just want to mention for one slide that the issues that I mention here are issues that many of us in AI know that are important to get to. And there are some efforts to start. So I'll mention the progressive neural network that was introduced lately by Google DeepMind. And what they suggested is they had this very nice neural network that managed to learn Atari games. And originally, every time they took the whole network and relearn a whole new Atari game. So the network did only one Atari game at a time. Then they had this very nice idea that we want to have transfer learning. And transfer is one property that you want to do. If you look in the previous slide, in number 2, you want to use previous knowledge to solve new knowledge. So their idea was they will train the whole network on the first game, then they take a copy of a network, but retrain it on 2 and another one on 3. But what they'll do in addition to train input-output, they will use information, they will take edges from previous nodes, previously learned games, and will be able to use it in the current game. What they show that in some cases, when they do it, it helps them to learn faster the next game and also better because they got some greater idea from before. There are limitations, though. They have to add full network at any new task, so it's not really scalable. Also, the system have to be told when the new task started, which is also something we do not want. And the other thing, it only works sometimes, and we would like it to work more in general. So I did not bring it in order to say that it's not good. It's wonderful. The community is starting to think about this issue, and what we want to do in this program is to actually give ourselves this very clear way of going forwards toward the direction that we are getting ready to. So in technical area 1, we're seeking a new chapter of AI. We want to think about new structures that modify their own rules, possibly a new type of neural networks, so that in 4 years we'll have this type of AI. And we have the 4 core possibilities, capabilities, and in phase 1 we'll have proof of concept for 2 years, and then the other 2 years we'll want to think about generalized lifelong learning solutions, which means that in the first part of the program, you will bring your own demonstration tasks and show us how it works in your own domain, so that your focus will be on the lifelong learning rather than in domain. And in the second one, you'll make sure that your solutions are general enough so that they can work on new domains that we will come with together, you and us, how to make it more general so it can work further on. So here you see various examples of demonstration application, anywhere from drones to cars to cameras to toys for a cat. And we'll accept everything as long as it can demonstrate the 5 core capabilities. So we'll be able to see how we did before lifelong learning and how it's doing after your algorithms for lifelong learning. So let's move to technical area 2. Technical area 2 is about transfer natural mechanism into AI. And we think about it as having 3 steps. First, we study the new mechanisms from biology or other physical domain, these mechanisms that support lifelong learning and have not been yet applied to machine learning. This is the study that you do. Then we transfer this mechanism into lifelong learning algorithms, and then we demonstrate it by checking how these algorithms are doing and quantifiably check and demonstrate how they improve performance. So as this is a 6-1 programs, it is okay to do wet lab research. It's also okay to do modeling and literature study. So you can decide how much you want to study the new mechanism and how much you want to take knowledge about mechanism that you already learned about them before and focus more on the transfer. So since technical area 2 is about new mechanism and core capabilities, we really think about it as giving you a free playground to play in the computational biology regime, as long as you remember that this playground will have to end with an algorithm, and this algorithm will have to solve one of the 5 core capabilities. So you will not have to do the whole system, but one of the core capabilities will have to be done better than it's done today due to your mechanism that you taught us from your domain. There is one other piece that is very special to this program, and we call it the center group. And the center group is not related to phase 1, phase 2, and is not related to TA1 and TA2. It's actually a center group for the whole project from the very beginning to the very end. And the way that we write it is develop future L2M community leaders. So the goal here is to encourage cross-pollination of emerging approaches to share expertise between biology and computation and have unique training to the members that are in the center group. So we think about the members of the center groups as becoming the leaders because they will put together notions from math and algorithms, energy, reliability, and will have specialized training and will put all kinds of ideas together. And we will meet very often in Arlington so that together we'll study this field and see exactly what's needed. The members of this will be me, government experts, and one technical representative from each performer. We typically think about that person that you'll bring as a person that is mature enough and knowledgeable enough and analytical enough so that it can represent your group and what you do. But it can be a young person. It can be a person like a postdoc that is just in a time that does not have to teach or to be in all the time at work and has the time to do the heavy travel. And clearly we will be paying for the travel and the expenses, so it's not something that you have to worry about. Now the approach is this: we'll share program level experience and insight to develop collective understanding. And collective does not mean that we'll have to include proprietary data. It will be more like the level of conferences. And the output that we consider for this group is cutting-edge results, new collaboration, evaluation paradigms and metrics. Think about it, how hard it is to have metrics to lifelong learning. So this is something that we'll do during the program. You'll do some in your BAA, and we'll continue developing it with all of you, in particular in the center group. And the other part that we'll do is this common test problem that will be ready for this second phase, where all of you will be part of it, either directly or through your representative in the center group. What is outside of the scope of the project? So we really want to study structures with life circumstances and change the behavior. So we are not looking for everything else. We're not looking for all these wonderful things in AI and machine learning that are already working very well and that are funded by other agencies and other programs. So we're not interested in incremental improvements. We're not interested in taking methods of current neural networks and just add something that does not scale, like simplified solution, growing number of tasks, something that does not scale with resources. And we're also not interested in philosophical approach, like what one should need to do, what will be a good idea. We're actually interested in having algorithms and having systems at the end of the 4 years. So with that, please look at the useful links. We have the broad agency announcement. We have also a lot of frequently asked question document that we continue answering. So please look at that. We also have teaming websites to the ones of you that think that you need particular assistance. And I would like actually to answer one of the frequently asked questions because it was asked so frequently that I would like to put it here. So not all of you have to go and look for it. And the people ask me, what's the size of the team or how much money to ask for? So the way we think about it is the following. You read the BAA, and the BAA is the document, not my presentation. You go to everything that I wrote in the BAA. You design a very, very good answer to this BAA. And once you do it, you see how many people you need and what you need in order to do that. And then you write your cost analysis fairly and honestly so that you cover it. So there is not anything about team size and not anything about money size. So with that, I would like to thank you for being with us. and joining these important people that already saw how important it is to do lifelong learning. And thank you very much. I hope to read your answer to the BAA very soon.